Alright, so I'm doing the skier problem for quiz 4D, and I'll start by introducing the problem. An 85 kilogram skier starts from rest at the top of a hill that is inclined at 33 degrees with the horizontal. The hillside is 200 meters long and the coefficient of friction between the snow and the skis is 0.075. At the bottom of the hill, the snow level and coefficient of friction is unchanged. What is the speed at the bottom of the hill, and how far does the skier move along the horizontal portion of the snow before coming to rest? So, what we're given at the start is our mass of the skier, which is 85 kilograms, and they start at rest, so their velocity is at 0. The distance of the slope is 200 meters. And the angle of the slope is 33 degrees. Now, that's labeled as theta 2, and I'll explain in a few minutes why that is. And the coefficient of friction between the snow and the skis is 0.075. And the final velocity of the skier is 0 because they come to a stop. So what are we looking for? We're looking for the speed at the bottom of the hill, which is the skier's velocity. Okay. So we need to figure that out. Well, in order to figure that out, we need to remember that the conservation of energy is used. But there are a few other unknowns that were not given that take some time to figure out. Well, we don't know the initial height. So in order to figure that out, we had to take the hypotenuse and multiply it by the sine of the angle, which is 33 degrees. So our initial height came out to be about 109 meters high. So let's start out with the conservation of energy. So the energy before must equal the energy after. Well, what kind of energy are we dealing with? Well, there's the initial potential energy, the initial kinetic energy, and we've got the final potential energy at this spot, not the final potential energy, but the potential energy at the bottom of the hill, the kinetic energy. And because there's friction involved, we also have work due to that friction being done. Well, what is work? Work is just a force times the distance times the angle. Okay? Well, what forces are being acted on the skier? We'll do that orange. Okay, well, we have the normal force, okay, which is perpendicular to the direction of motion. Well, we have gravity, which is always straight down. It's not perpendicular to the motion. So, and that's just Fg equals mg. Okay. We have friction because of the snow and the ski having friction. And then we just bring this down. Okay. And this is theta 2 right here. So we've got the mg, and this is the cosine of theta 2, and then this is the sine. Do not want to write that. Oh no! fix it. There we go. Sine of theta 2. Okay. Well, now that we know the forces, I need to explain the cosine of theta 1. Well, the cosine theta 1 is 180 degrees. That is because the force of friction is parallel to the direction of motion. And when that happens, it's 180 degrees. We don't use this 33 degrees, at least not yet. So let's change back to my original color. Okay. So FF times D1 times the cosine of 180. Cosine of 180 is just -1. Okay. So, but what is FF? FF is just the coefficient of friction times the normal force. Okay, but the cosine of 180 is equal to -1. So we have a negative right here. Well, what is Fn? Fn is just is this right here. It's mg cosine of theta 2 times the distance. So that is your work. Hey, so now that we have work figured out, let's minimize this. No. Undo. So we'll come back for that later. We'll put it up here. Okay. Now that we got that out of the way, let's figure out what types of energy can cancel out. Okay, so our initial potential energy, okay, that involves height. Now, our initial height is 109 meters, so we'll need that. Our initial kinetic energy, well, that involves velocity. Our velocity is 0, so we don't need that. Our final potential energy, well, our height is 0 at this point, so we don't need that either. Kinetic energy, well, we need that because we're looking for the velocity, and we just figured out work, so we definitely need that. So that's too big. Potential energy is the mass times gravity times the initial height. Okay, that's the energy before. Now the energy after is 1/2 times the mass times the velocity squared. That's velocity 1 plus this guy right here. Now we get rid of the negative because gravity is considered negative, so we just make that positive. So we've got mu k times mass times gravity times the cosine of the second angle, or theta 2, times the distance 1. Okay, so what are we looking for? We are looking for this guy right here. So we need to single them out. So let's solve for velocity. We're going to subtract this whole thing right here. Okay, so we've got our potential energy minus our work. And that's equal to 1/2 our kinetic energy. Okay, we can multiply by 2 on both sides to cancel out this 2. Okay, 2's right there, and then we can divide by the mass. Okay, so we're left with our velocity squared 2 g over our mass. Well, I kind of see that mass and gravity can be taken out of the parentheses, and they look like they can cancel out with the bottom. So I'm going to do that and make a little less work for me. So we're left with 2g. Oh no. Times the initial height minus coefficient of friction times the cosine of theta 2 times the distance. Okay, well, we got to get rid of the squared, so how do we get... Oh, that's not what I wanted. How do we get rid of that? Well, we take the square root. So, in order to find the velocity, we need to take the square root of 2 times gravity times the initial height minus the coefficient of friction times the cosine of theta 2 times the distance. Now, all we do is just plug in our numbers. So 9.81 meters per second squared times, what's our height? Our height is 109 meters minus coefficient of friction 0.075 times the cosine of theta 2, which is 33 degrees, multiplied by 200 meters. Okay, and our final answer comes out to be 43.478 meters per second. Well, we need to consider significant figures, so 43.5 meters per second. And that is our velocity. So let's put that in. Let's erase this. Put that in right there. So 43.5. Oops. Too big. Still trying to figure this thing out. So 43.5 meters per second. Okay. Now we figured out the velocity. What else do we need to figure out? How far does the skier move along the horizontal portion of the snow? Okay. what is that? Well, that is this distance right here, and we're going to label that as D2. Okay, so in order to figure that out, we need to consider conservation of energy. Okay, so we've got our energy before equaling our energy after. Now, I'm going to use the initial energy, okay, because that'll help us solve the problem a little bit easier. Okay, well, what is our initial energy? Well, we've got our initial kinetic energy plus our initial potential energy, and that's going to equal our final energy. Okay, well, if you noticed, the coefficient of friction still remains during this time, so it's still performing work. So for this problem, we're going to consider our first work due to friction and then our second work due to friction. Okay, so let's figure out what cancels out. Well, we know that the kinetic energy is 0 because there's a 0 initial velocity. Okay, so but we do need the initial potential energy because we have a height up here. We're going to use that to solve the problem. So our initial potential energy is just mass times gravity times the initial height. Okay, and then this guy is this up here. So it's going to be, oh no, what happened? It's just going to be the coefficient of friction times mass times gravity times cosine of theta 2 times the distance, the first distance, plus, well, what is this guy? Well, we do know that friction is being performed. So I'm gonna write this work down here. Okay, so same thing, force times distance, but we're doing distance 2. Okay, and it would still be the cosine of the angle. Well, friction force is parallel to the distance. So we know the cosine of 180 degrees is just -1. So we just have FF times D2. Well, what is FF? It's the coefficient of friction times Fn. Well, we already learned that earlier, that Fn is just mg. Okay, we don't have an angle here, so we don't really need to include that. So this is what we're going to take down here. So it's going to be coefficient of friction times the mass times the gravity times distance 2. Well, what are we looking for? we're looking for this distance right here. Okay, so we need to get this guy by himself. So let's solve for D2. Alright, so we're gonna subtract this whole thing. Okay. Cosine of theta 2, okay, equals UK mg d2, okay. We divide to cancel these guys out. Okay, well, I noticed something here. The mass times the gravity is in all of these, so I can technically just cancel these guys out. So what am I left with? I'm left with d2 equals the initial height minus coefficient of friction times the cosine of theta 2 times the first distance, all divided by the coefficient of friction. Okay, so now that I solved for D2 symbolically, all we have to do is just plug in our numbers. So D2 equals our initial height. What is that? That is 109 meters. Minus coefficient of friction, which is 0.075, times the cosine of theta 2, that's 33 degrees, times our first distance, and that's 200 meters. And that's all divided by the coefficient of friction. So D2 is equal to 1,284.636 meters. Well, we need to remember sig figs. So about 290 meters. And that's it.